Hello, welcome back to NMI. In this video, I'm gonna show you a crazy idea that I had some time ago. It's a different power supply for the Commodore 64. The reasoning behind this power supply was basically the fact that the aging power supplies that are the original ones are aging and failing, and when they fail, it's a catastrophic failure. They usually short and the regulator, and then the higher voltage fries the whole machine. So that is one of the reasons. The other reason, I know that there are other off-the-shelf power supplies out there, but I wanted to design one without a bulky transformer. So that is what I'm gonna show you in this video. So come with me and let's take a look. Warning: the design you're about to see is experimental and not certified in any way. There are several areas of this circuit directly connected to mains, 120 volts AC, and that voltage can hurt you badly or even kill you. Do not try any of this if you are not sure of what you are doing and understand the risks. As I mentioned in my previous video on the Commodore 64, the power supply on these machines has two different voltages, plus 5 volt DC and 9 volt AC. And the reason for that is that it derives internally from this 9 volt AC derives different other voltage like 12 volt, 9 volt unregulated, and plus 5 volts. And it also derives a clock signal from the AC that feeds the CIA the time of day timer, right? So that is the reason that it's not easy to replace the power supply with any off-the-shelf power supply, because you need AC and DC, right? Here we have the current design, right? How the standard 64 power supply is designed. We have a 5 volt DC power supply and a 9 volt AC. They're both derived from the same transformer, so it has two secondaries, one for the 9 volt AC and another one for this independent power supply. One thing that we can see, and we can also see from the schematics, they do not share the same ground. That is a very important thing. The grounding of the two power supplies happens inside of the C64, and this is where the challenge is. So what I'm proposing in this project is to replace the standard power supply with a more reliable version and modern version using two switched power supplies, right? One for 5 volts, pretty ordinary, and another one that is going to provide the AC. But then you're going to say, oh, but a switched power supply is DC, right? And I know that. So we're going to use a trick here. We're going to use an optocoupler and an H bridge to alternate this power here from this other power supply. So we keep alternating the voltage, and then we're going to create a fake AC, right? For the 64, it is still AC. Maybe it's not the right one, but it's still AC and enough to make all the voltage doublers. And as I explained in the other video, there is a voltage doubler there and all that circuitry is expected to work just fine with this fake AC, right? The optocoupler here is gonna get its input directly from the line voltage, so we're gonna use a large resistor here, and I'm gonna add some more protection, of course, but that is basically the idea. Here we have the first design that I did. This was using the DRV8220. I thought it would be a good idea because this is a small electric motor driver, and I thought it would be good enough and simple enough, but we don't need to go there. But I realized that this first, let me show you the PCB. So this is the DRV8220. It is extremely small, very hard to solder by hand, and on top of that, it doesn't have enough power, right, to provide the required AC current here. So I'm not gonna show you all that, but I did a lot of testing and I built boards, and the performance was not the expected, right? So that leads us to version 3 and version 4. Version 3 is using an L298. I'm gonna show you a video. Before I built this board, I made some tests to make sure that the L298 would work as I expected. It's basically the same principle. But we need a 5-volt regulator here to provide the pull-ups and the power for the logic side of the L298. I connected the two, because it has like 2 channels, so I connected them together. Oh yeah, and let me explain how the line synchronization happens. So we had to add 2 optocouplers because the L298 truth table expects in 1 and in 2 to alternate in order to alternate the outputs. So we have 2 optocouplers. One is driving high or enabling the positive cycle of the sine wave, and the other will enable the output when it sees the negative cycle of the sine wave. So this is why we have the diodes in the opposite direction. I also added the Zener here, a 12-volt Zener. So these LEDs, they only switch on at like a slightly higher voltage. So that is gonna give them space between the positive and the negative semi-cycle. And a large resistor here, 36K, that is gonna dissipate most of the energy, right? Because here the peak reaches 170 volts on the line voltage of 120 AC. So most of the voltage is dissipated here, most of the power. So there's a large voltage drop here, plus the voltage drop on the diodes and on the Zener and on the junction of the LED. That's basically it. So this is how it works. So the output of the optocouplers, you have square waves, digital square waves, right? And that's it. Now I'm gonna show you the testing of this circuit, and then Oh yeah, but let me show you the PCB that I designed for this. Let's turn on everything. So it's quite small. Here you have all the AC side, which is higher voltage, and then on this side is lower voltage, and the optocouplers here, so they provide the reference signals for the L298. Here you have the 5-volt regulator. This is the 5-volt output. This is the AC output. We have two LEDs that show here. I'm not sure you can see the cursor. Yeah, here you can see the LED that shows that we have 9 volts, and here the LED that shows 5 volts, right? So I'm gonna show you the testing, the prototyping or pre-prototyping, right? Before I even built this board, just to proof of concept to make sure that everything would work fine. Yeah, as you can see, this board was designed last year, so it took me a while to put everything together. I was busy. Yeah, so let's take a look and see the. First, I'm gonna show you the proof of concept of this, and then the building of the board and testing. I'm not sure it's gonna fit all in this video. Probably we're gonna have to split it in two, but I think it's gonna be fun. This is the PCB, the latest PCB that I designed end of last year. This is the version 3 of this PCB. It uses the L298, as I mentioned when I was showing the schematics. And well, we already covered all the design there. So now we're gonna assemble it and make sure that it's working. We're gonna start with the SMT components. Maybe the top first and then the bottom. We have components on both sides of the board. So we have the rectifiers and like diodes here. There's a capacitor, the fuse, and some resistors here, and then more resistors, capacitors. So let's start with this diode. Yeah. Okay, so the PCB is mostly assembled. Now the last part is the L298 that we're gonna solder right now. Okay,
Now this should be good, I guess. Yeah, and the board is ready. Now all we have to do is to connect the power supplies and we're good to go. For this one, I'm not too sure, but I think we need to use a 12 volt because the voltage drop here is higher. We're gonna check that out later.
If we use a 9-volt switched power supply, due to the voltage drop inside the L298, we're going to be too close to the minimum voltage that is expected on the regulators inside the Commodore 64. So I decided to use 12 volt instead. It should be more than enough, not too much, because when you use the standard or the power supply that comes with the Commodore 64, it provides 9-volt AC, but the peak voltage is around 12.6. So that means that when you filter that to DC, you get 12 or 13 volts. I'm gonna show you also in the video, so we should be fine.
I have finished assembling the board, and here's the final result. I have the AC connection here. I'm not using the ground right now. It doesn't matter for now. Here's the new PCB that I assembled, the version 3. There was a version 2, but it had an issue, so that's why we are using now version 3 here. We have the two power supplies here, one 12 volt 2 amps and another 5 volt 3 amps. So they are both connected to my PCB in the center here. As I mentioned before, the reason we are using 12 volts here is the voltage drop on the L298. What else? I checked all the connections. We can see ground connected to the ground output here and here. Positive here connected to positive there. Same here. The two AC inputs connected to the right AC inputs on each power supply. Everything looks good. Now it's the moment of the truth, right? The smoke test. Wish me luck. Okay, we are now ready to go. I'm gonna plug in the AC power, and hopefully there won't be smoke and explosions. So fingers crossed. Yes! Look at this. Let's see, we should have 5 volt, but that is pretty ordinary. Yeah, 5.14. And if we switch to, well, we don't need to measure. We can see on the scope. Yeah, let's use the scope. That is silly. On the scope, we can measure here. Frequency 60 hertz, RMS 11.7 volts. The peak is 13.2. That is higher than I expected. Let's use the cursor to measure voltage. Yeah, the peak is 12.4. Oh, that's probably because there's no load. Yeah, that must be it. Because there's no load, then the voltage drop on the L298 is not playing a major factor, but we can see here. So here it's pretty cool because this is the transition between phases, let's say. So it's working as expected, right? Now let's decrease here the, yeah. Now the next step, I'm gonna bring my Commodore 64, the testing board. I have one that is not working, so we can remove all the chips just for the sake of safety, right? We don't want to damage any of those very hard to find chips. So I'm gonna make that test and we're gonna measure in circuit all the parameters.
Well, that's it for this video. In the next one, we're gonna make all the testing and we're gonna see if this power supply is really working or not. So stay tuned and see you next time. Bye!